we're going to be doing problem 2a, first problem on midterm 2. And we're told to find the incident H field given these numbers. So I'd start off with the givens. So we got 15.92 gigahertz. Okay. We have E of I at 10. So is going to go, so using right hand rule, we have X, our fingers pointing this way, our Z, our thumb pointing up, and then our Y, using our right hand rule, our Y, where our palm is going to be pointing into the page. So this is our X, this is our Z in a three-dimensional way. So it's going to be going into the page, our right in. So it's clear for people. Okay, our E of R is equal to 81, U of R equals 1, and this is equal to 0.4 for water. Okay, so this is given as E of I. Okay, using a rule, E cross H equals K. Using our thumb as K, our thumb will be for this, fingers for this. We can find where H is pointed at. So using right hand rule again, thumb is going along this line here. Then am I letting with my pointer, and then our E is going into the page. So our H is going to be pointed out this way, perpendicularly. So that's a perpendicular. And we're going to want to draw little coordinates here, because that's going to be important when we solve for the H of 1 and the H of 2. So the next part is that H1 cross H2 is equal to K. So H1 is going this way, our K is going this way, our H of 2 is going to be going out of the page. So out of the page. So we should expect that H of 2 is going to be in the negative Y direction. Okay, because in this problem, Y is going into the page. Okay, so with the givens, let's start finding some variables that we need to use. So let's do E of I of 1 is equal to the Y hat at E naught cosine of omega t minus K and R. I like calling it R as like a R vector, and that's what I'm used to, because when we do attenuation, there's alpha and then R. So I like calling it that. So, okay, with the givens, we have 15.92 gigahertz. Okay, let's remember that giga is equal to 10 to the 9. Okay, kilo is 10 to the 3, and mega is equal to 10 to the 6. Even in midterms, some people get it wrong and they end up getting a different material and end up doing the whole problem wrong. So make sure you remember these, alright? Giga is 10 to the 9. That's very important. Okay, so 15.92 times 10 to the 9 multiplied by 2 pi. Why? Because omega is equal to 2 pi f. Okay, so that's going to get us our number, our K is going to equal to what is it, 10? Not our K, our mega is going to equal to 10 to the 11. So our mega is equal to 10 to the 11. Okay. K is a whole different thing. So K is given as omega over V. That's the official way. But V is equal to C over N. But since we're in air, N is just equal to 1. So this is simplified to K equals omega over C. But it's good practice to remember this and not just assume that K is always equal to omega over C. Okay, so we have to also remember that there's this N term there. So it simplifies to that. So we have 10 to 11 over 3 times 10 to the 8. That's going to get us the number of 333.333. That's what we're going to get. Okay. And then we're going to be working, not 3,000. Oops. I put an extra 0 in there. 333. So this is going to be our K value. Okay. And do we have everything? Our R. We do not have our R yet. So our R is what I like to call direction. So if this is 37 degrees, okay, and we from where we learned geometry that this angle is also going to be 37 degrees. If this is 90, this is going to be the opposite. So 50, not the opposite, but the supplementing part of it. So 53 degrees, okay. And we're going to use, we can either use this angle or this angle, but for this one, I'm going to choose the 53. I'm going to use actually I'm going to use 37. Less work. So we know this angle there is the same. So let's start getting it. So we should see a negative x, and we should be seeing a negative z. Okay. So that's how I get my directions first. So we have a negative x. Our negative x respect to the angle is the cosine of it, is adjacent. So we have cosine 37 degrees. And we have negative z, sine. It's going to be the opposite. Okay. So it's the opposite of the angle. So we have this opposite component of it, 37 degrees. Okay. Plug those into the calculator. We have a value of around 0.8 x hat minus 0.6 z hat. Okay. So those are going to be our values for our little r direction. Okay. Next, EI of 1 is going to be written as, oh, there's no hat in these. Let's get those out of here. We're going to have y 10 cosine, okay, (10 to the 11t) minus this k. So we have 333.333 multiplied by negative 0.8x minus 0.6z. Okay. Alright, EI of 1 is just going to be y 10 cosine 10 to the 11t. We're going to have plus 267x plus 200y. Not y, z. Okay. Now, going from that to h, okay, looking at the equation cheat sheet, we should see that h is equal to, our h1 is going to equal to, so we're going to need the direction part of it, e over eta naught, because we're in air. Okay, let's write that in red so remember that we're in air. When we're not in air, we're going to be using, we will need to use n, the n term in it, but since we're in air, we're going to keep it this way. Cosine omega t minus k r. Okay, this is in air. Okay, next we're going to have h1, the direction of this. Alright, now we need to start finding these angles. Okay, this is 53. This is 90 again, since it's perpendicular. This is going to be 37 degrees again. So Alright, so different numbers. So we're going to have a positive x component but a negative z. Okay, so we have x. The positive x is the opposite, so it's positive x sine 37 degrees plus negative, oh, it's not plus, minus z. Okay, let's not forget the hats here. These are unit vectors. Cosine of 37 degrees. And we're going to have our e, which is just 10, and eta naught. And remember, eta naught is given as 377. All right, it's good to remember. Next, we're going to be having the phase part of it. So remember that E and H are always in phase. So we have 10 to 11 t plus 267x plus 200z. Okay. Also remember this is volts per meter, and this is going to be amps per meter. So calculating all of this, we have x hat of 0.6 minus z hat of 0.8 multiplied by 10 divided by 377. Okay, this is going to be same down here, so let's just duplicate it. Okay, that's going to come out, crunching the numbers, we're going to have h1 of I, the incident, is going to be x hat 0.0159 minus y 0.021 cosine of that. So we're going to have cosine of this. Okay, it's going to be amps per meter. Alright, next we're going to need h2 of I. h2 of I is going to be this one that we found here. Should be in the negative y direction. So we're going to have negative y here, negative y hat. Negative y hat. And then we're going to have this 10 up here. It's going to be the same thing pretty much. So we're going to have e over 377. That's going to be sine. Again, they're in phase. So this, all of this, same again. Okay. So these problems are easy once you get the hang of it. Okay. Negative y, 10 over 377. Sine. Okay. All that jibber jabber. Negative y, 10 to 377. Oh, already wrote that. Calculating that. Let's see. Okay. 0.0265 sine of 10 11t plus 267x plus 200z amps per meter. Okay. h2 of I. And that's it for finding the H incident for both of these.
We will be finding the reflected H field now. So when working with reflected or transmitted, we need to work with the loss tangent. And that's an important part of problems like these. So loss tangent is given as sigma omega epsilon, sigma omega epsilon naught, epsilon r. That's what this is made out of. It has two parts. So this is going to be 0.4 over 10 to the 11 multiplied by e of 0, which is given as 8.8 something, but I like to use 10 to the negative 9 over 36 pi. epsilon r is 81. So we're going to have a 0.005 low loss. It's important to know that when doing problems like these, it is never ever in between 0.01 to 100. Okay, we do not work with general materials in this class. No general material, not good. Okay, so with that, we need to use Snell's law to find the gamma. So using Snell's law, we have n of incident, sine of incident equals n of t, sine of t. So 1 in there, sine of incident is going to be 53 degrees because Snell's law, we need to use the angle that's normal to the plane. So this is our thing down plane down here, and this is normal to it. So we're going to be taking this angle here, 53 degrees. So n of transmitted and is going to our n of t. Our n of t is found through E of r. So n is equal to the square root of E of r. And the square root of E of r is going to be 9. So we have 9 sine of t. And like that, we have everything we need to find the angle. So the angle of t is going to be the sine inverse of sine 53 degrees over 9. And that's going to give us a 5.09. And this can be our angle transmitted. Okay, so gamma perpendicular is given as n1 cosine I minus n2 cosine of t. And on the bottom is going to be the same thing. Plus n2 cosine of t. The only difference is that they add each other. So for gamma per parallel is going to be the same thing, but n of I cosine of t minus n2 cosine of I. Only the thetas swap. And on the bottom is going to be plus, and the same thing is reflected down there. So we're going to have cosine of 53 minus 9 cosine of 5.09. The bottom part is going to be just the sum of those two. The top is the difference, and the bottom is the sum. So on the bottom, we're going to have cosine 5.09 cosine of 53 degrees. And we're going to be adding those up together. So calculate that, we're going to get negative 0.874. Okay, and this is going to be negative 0.689. And our gammas are found. And that's going to help us on finding the reflected H field. So let's find the R of this one. We found the R earlier on this. We need to find the R in this now. So the R is still going to be in the negative x direction, but it's reflected up. So we should be seeing a positive z, negative x. So let's figure that out. We have negative x cosine of 37 degrees. We're going to be using this angle here. So the opposite is going The x is in the cosine component, so it's going negative, and then the z should be plus z hat sine of 37 degrees. And that's going to equal to negative 0.8 x plus z 0.6, and multiply all that by the same k as we found earlier. So looking for the h reflected and e reflected, we're going to be using e of r reflected to find the h reflected. So of y hat 10 multiplied by the gamma perpendicular cosine of 10. Because they're in phase, all of this is going to be the same, minus 200z. Doing the math, ER of 1 would equal to y hat 8.74 cosine 10 to 11t so that's our E of R1, negative, because from the perpendicular gamma. To find HR of 1, we need the direction, the E naught, gamma perpendicular over eta naught, because we're still in there, as seen in this diagram. This is air up here, and water is down here. We have cosine 10 to 11 plus 267 x minus 200 z. So by doing the math, we already know the direction is going to be in the negative y direction, and that from reflection we go from right hand or RHCP to left hand circular polarization. So our E is going to be going out of the page. ER of 1. And using our left hand for this right hand rule, we're going to have K going up, but E is pointing out. So our H is going to be pointing down this way. So this is our HR of 1. And our HR of 1, if this is 37 degrees, this is going to be 37 degrees. You can also see that these lines are parallel, and these are angles that are going to be the same, so this is 53. So that makes a 90, and the remaining is going to be 37 here. So we have 37. So we're going to use trigonometry to find these angles here, to find the x and y component. So our HR of 1 is going to equal to negative x sine of 37 minus z cosine of 37. And then we're going to have our eta naught and gamma. So 8.74 over 377. And cosine of the same stuff, because it's all in phase. We're going to get negative x 0.6 minus z hat 0.8 0.74 over 377 cosine. Plugging that in the calculator, we're going to get x hat 0.0139 plus z hat 0.0185 cosine 10 to 11 minus 200z. And that's going to get us our HR of 1. Next, we need to find HR of 2. So HR of 2 Using our left hand to find the HR of 2, we're going to have K pointing, our thumb is going to be pointing this way. Our fingers are going to be pointing down, so we know that our HR of 2 is going to be into the page in the Y direction. That's our assumed. So our HR of 2 is calculated using the direction eta naught gamma 377 sine 10 to the 11t plus 267x minus 200z. Okay, so we have y hat, and then we have 10 multiplied by the perpendicular, which is negative 8.74, over 377 sine of 10 to 11t plus 267, and our HR of 2 is actually going to be in the negative y direction. Negative y 0.0182 cosine of 10 to 11 t plus 267x minus 200z. And that's going to be our HR1. Oh yes, and these are in amps per meter. I forgot about that.
We're going to be calculating for transmitted E field. Okay, so we have many things we have to find, like alpha, the attenuation term, eta, k, transmitted perpendicular, and transmitted parallel. So we're going to start off with finding alpha equation. So we're going to get sigma over 2 eta. And remember, when eta is inside a medium, we're going to have eta naught over the index of refraction. So n is equal to the square root of ER. So that's going to be square root of 81. We're going to have 377 over 9. So 0.4 over 2 multiplied by 377 over 9. That's going to give us a value of 8.83. 38. Next value we're going to look at is the tau. Tau perpendicular is equal to 1 plus the gamma perpendicular. So that's going to equal to 1 minus 0.874 from the gamma that we found earlier. So that's going to give us 0.126. Next is going to be finding the tau of the parallel. So tau parallel is going to be n2, eta 2 over eta 1, and it's going to be 1 minus gamma parallel. So eta 1 over eta 2, we're going to have 377 over 9 divided by 377 over 1, and that's just 377. So 1 minus gamma parallel. Dividing that, we're going to end up with 1 over 9 multiplied by 1 minus the gamma parallel. So that's going to be plus 0.689. So that's going to be 0.188. This is enough information to start looking for our E of t. What else we have to know is that we need to know this k direction. So let's write this whole equation out. So we have y hat, because all of the e's are going to be in the same direction. So the E is going to be going up here. Using our right hand rule, we have going down into the page, and that H, that E2 is going to be going that way because it's right hand circular polarization. But we're going to do this first. So we have tau perpendicular eta naught, E naught, the attenuation term, R cosine of omega t plus the K and R. I like calling it R, but so this is going to be our R here, this one going down here. So let's try to figure that out. So, yes, also we need to find K. K is equal to omega over V. V is equal to C over N, and then by replacing that, equals omega over C over N, we're going to end up having omega N over C. So that's going to be 10 to the 11 multiplied by 9 over 3 times 10 to the 8. That's going to get us around 3,000. Next, we need to find this R value. So R value is just going to be this one right here. So we have a negative cosine component, negative. So this is negative x, and we have a negative z component. So let's do that. So our our R, I'm going to write it as negative cosine 5.09, and then we're gonna, and that's in the x hat direction, and then we're gonna have a minus sine of 5.09, and that's gonna be in the y direction. No, negative z. Right, this is gonna result us in having negative 0.089x minus 0.996z. That's going to be our R. Okay, and then we're going to write all of it down. So y hat, we're going to have tau perpendicular of 0.126 multiplied by 10. Our attenuation constant, which is, no, there should be no hat here actually. And so attenuation term of 8.38. We have an R value of negative 0.089x. This R just goes right into there. 0.996z. Okay, and then we're going to have our cosine, omega 10 to 11t plus 3,000 multiplied by this R value. And when we plug that in, our ET of 1 should equal to y hat of 0.126 of 12, 1.26, yes, E, and distributing this, we're going to get two negatives, so we get a positive 0.746x plus 8.35z. Next, our cosine term, 10 to 11, same thing, they're in phase, so we have there should be a minus here. So this minus 3,000 distributes into the R, so we're going to get a plus, so 3,000 multiplied by 0. Multiplied by, well, let's remember it's negative 3,000 multiplied by negative 0.089 x, so we're going to end up with 267x and then 3000 multiplied by that, so 3000 multiplied by 0.996, that's going to end up with 2988Z. And this is in volts per meter. So that's our EAT of 1. And then let's move on to ET of 2. Should be the same process, fairly simple. But this time the direction is a little different. So from Snell's law, we know that this is 5.90 angle. So using these little like dashed lines here, we know this is like a similar triangle. So this is 5.09. This is 90 degrees. This right here is also 90 degrees because it's perpendicular. So this is going to be a value that's not this 5.09. So, and we'll just call it x. If this value is not 5.09, then in this right triangle where it has to add up to 180, this will be the 5.09 angle here. So using this angle, we can find the direction for that one. So the direction for that, we're going to have a positive x but a negative z because it's going this way, positive x, and it's going down. So negative z. Looking at the angles, we have a cosine of x, cosine theta, and then the x, and then we have a negative sine of z, of theta, and a z component. So let's write that down. So we have a x hat cosine of 5.09 minus z hat sine of the 5.09 also. And since this is ET of 2, this is going to be parallel with the incidence, plane of incidence. So we're going to be using transmitted parallel, EI of 0. The attenuation term. The attenuation and the phase is going to be the exact same from ET of 1 to ET of 2. So we have to remember that these things are in phase, and the attenuation term is going to be the same. So we can just copy it right down. Plus 8.35z sine 10 to 11t plus 267x plus 2988z, again, volts per meter. And then we just need to figure out this part of it. So simplifying this, cosine of 5.09, let me calculate that. Cosine of 5.09, we're going to have 0.996, let's put that in the x hat, minus sine of that. That's going to be 0.0887 multiplied by the gamma parallel, which is 0.188. E of I, that's going to be 10. And then we're going to have the rest of our term. So plugging that into the numbers, we're going to have, so in the x, we're going to have 1.87 about x hat. And then we're going to be subtracting, this is the z. Let's not forget the z hat. We're going to have 0.17 z hat. So this is going to be our direction. E 0.746x plus 8.35 sine of omega 10 to 11t plus the 267x plus 2.2988z volts per meter. Remember, both of these, when dealing with E field, we're going to be having volts per meter, and when we have H field, we're going to be working with amps per meter.